Question 9. Carbon 11 is radioactive and decays by beta plus emission to form boron. Carbon 11 has a half-life of 20 minutes. Boron 11 is stable. Define half-life. Here I just defined half-life by saying half-life is the time taken for the activity of a sample to halve. I will not define what is activity at this age, but it could also be called time for the number of nuclei present, or for the initial number of nuclei to halve. It can also be said to be the time for the count rate to halve. A sample contains N0 nuclei of carbon 14 and no other nuclei at time t is equal to 0. Sketch on fig 9.1. Sketch the variation with time t of the number of nuclei of boron 11 in the sample. Now remember, boron 11 is the one that is being formed by the decay of carbon 14. And one carbon 14 nuclei decays to form one boron nuclei. This must be clear. So we want to know if the sample contains N0 number of nuclei of carbon 14, it means that at first at time t is equal to 0, here at time t is equal to 0, here there was no nuclei of boron 11 present. So we are given that the half-life of carbon 11 is 20 minutes, as is said here. So if half-life is 20 minutes, it means that in 20 minutes we expect half of carbon 11 to have decayed, to have formed. So half of carbon 11 to have decayed, meaning that of the N0 that is present, 0.5 N0 will be left of carbon 11. But by the same measure, 0.5 N0 of boron 11 would have been formed. So after 20 minutes, we have 0.7 of boron, 0.5 N0 of boron 11. Now, if we go further an extra 20 minutes, from this 20 to this 20, that's another half-life. We expect of the 0.5 carbon 11 that is left, for that to decay by half, so that we are left with the 0.25. So in other words, the 0.25 would have been turned into boron during the next 20 minutes, meaning that now we have 0.75 N0 of boron 11. Then during the next 20 minutes again, we expect of the 0.25 to decay to 0.125 of carbon 11, meaning that 0.125 of boron would have been formed, and not. So meaning that if we add another extra 0.125, then finally in the next 20 minutes, and again of the 0.125 that is left of carbon 11, if it decays by half, it will form half of 0.125 of boron, which is 0.06 125. If you divide that one, that's 0.0625. which means that it will be half of that one, which will be somewhere here. So if you have to draw this graph, I think it's a nice curve that we can come up with here if we draw it nicely. So let me try to join every point. Okay, it didn't come out too well. I don't like that one. Let me come. Oh, this much better, but still. Okay, I can live with this one. Okay, but let me just keep the worst one, which does not get corrected for. Now that's the graph there. Now the question then asks, explain with reference to the random nature of radioactive decay why the activity of carbon-11 sample in B decreases with time. They're asking you, why does the activity decay decrease with time? Now, it is important for us to understand that activity, now by definition, not by definition, but even if you want to talk about activity as a definition, activity actually is the rate of decay, which we can say delta N over delta T. However, activity is also given by minus lambda N or lambda N, sorry. But the minus, we can ignore it. Or the minus simply means that the activity is decreasing as N is decreasing. So in magnitude wise, activity is equal to lambda N. But lambda is a decay constant. Lambda is the probability of decay of a nucleus. So this is where we start now with the random nature now. The random nature implies that the probability of decay of a nucleus is the same. Every nucleus which is present has the same probability of decay. Why? Because the decay itself is random. So by virtue of the decay being random, if anything is said to be random, for example, throwing a die is random, it's a random process, then it means that the probability of getting a 1, a 2, a 3, a 4, a 5, a 6 is equal because it's a random process. So that is the implication of us saying radioactive decay is random. One of the implications of radioactive decay being random is that the probability of decay of any nucleus is the same. Because it's a random process, we cannot predict which nucleus is going to decay next. So the probability of decay of any nucleus is the same. Now, the probability of decay of a nucleus per unit time, probability of decay of a nucleus per unit time is lambda. So it means that lambda does not change. Probability of a nucleus decaying doesn't change. It is not affected by how many nucleus are left. Probability of decay of a nucleus per unit time in a given time is not going to change. It's not affected by N1. It's a random process, by the way. So the probability of decay is not going to change per unit time. Now for context, because without adding time now, then it would be expected to change with time. But now if we say per unit time does not change, then that is more effective in the sense that we have clarified that after 1 hour, the probability of decay of a nucleus is still the same, despite that maybe there are now less nuclei present. No. What can be affected, of course, by number of nuclei present is probably the activity. But anyway, even if you go to the statistics a little bit, a random process is not affected by the fact that the number of trials have changed. For instance, take the probability of getting a head from a die. Each time, even if you do 20 tries, you throw a die 20 times, or maybe you toss a coin 20 times, the expected number of heads is 10. Why? Because the probability doesn't change of getting a head doesn't change. because you have thrown the die, you have tossed the coin once. The first time you toss it, it has a 50-50% chance. The second time you toss it, a 50-50 chance of getting a hat. Third time you toss it, a 50-50 chance of getting a hat. It's random. So this is the same thing with lambda, the decay constant, which is the probability of decay of a nucleus per unit time. It's a constant. It's the same for every nucleus, and it's also a constant. So now when nuclei are decaying, it means that n is decreasing. So if n is decreasing, then activity should also decrease, since lambda is a constant. So that's what this question is asking. Explain with the reference of the random nature of radioactive decay why the activity of carbon-11 sample in B decreases with time. So it is asking you, why is it that the activity of carbon-14 actually decreases with time? So the point was, every undecayed nucleus has the same probability of decay. So every undecayed nucleus of this left undecayed nucleus, the probability of decay is the same. It is the same throughout per unit time, the probability of decay. So uranium has this one probability of decay per unit time of its nucleus. It's decay constant. So since the activity is equal to A is equal to lambda n, as there are fewer undecayed nucleus remaining. So when n is decreasing, there are fewer undecayed nucleus remaining with time. So fewer will decay in a given time interval. So you are saying that if there are fewer that are left to decay, if the probability of decay, let's say, is 50%, but there are 20 left, the probability of decay in the next 1 hour is 50%, and there are 20 left, then in the next hour we're expecting 10 to decay. But if there were 100 left, in the next hour we would expect 50 to decay. So you see, the lesser the number of nuclei left, the lesser the activity being the rate of decay of nuclei, the number of nucleus decaying per unit time. State with the reasons whether a radiation detector placed near to the sample of carbon-11 indicates a measured count rate from the sample that is less than, the same as, or greater than the activity of the sample. So they are simply asking you, is a detector going to show an activity which is less, a count rate, sorry, because on a detector we get a count rate. Count rate is simply more or less us counting the number of alpha particles hitting the counter per unit time. So that's count rate. And alpha particles or beta plus particles are produced by the radioactive decay. So the question is asking you that whether the activity and the count rate are going to be the same, or the count rate is going to be more than the activity, and then, or the count rate is going to be less than the activity. Now, for you to think about this properly, you must understand that activity is the decay of all the nuclei present. So if there are not all the nuclei present, but the decay of nuclei per unit time. Count rate now is counting the radiation that is detected from these decays. So for instance, we can never expect the count rate to be greater than the activity. Why? Because if 5 nuclei decays in per second, let's say, then the activity is 5 per second or 5 becquerels. But the count rate can never be greater than 5, because it is going to count the gamma rays, the alpha particles or the beta plus particles that are produced, and the one decay produces 1 beta particle. So the count rate, we are never going to count more than 5 per second. Clear? So, but there's a problem in this case now, in this, that if this is the source of radiation and this is our detector, radiation, when alpha particles are being produced or beta plus particles or beta minus particles are being produced, they are not produced. The decay is spontaneous, number one. It happens as it wants. They are not told to decay specifically and go in the direction of this detector. So the detector can only detect those beta particles which comes near it or towards it. All these other ones which go in other directions, it cannot detect them. This means that what it counts is less than what has decayed per unit time, which means that the activity will be bigger than the count rate, or the count rate is going to be less than the activity. That's point number one. And point number two is that even among these ones which are going towards the detector, remember that they are moving through air, and as they are moving through air, some of them will be absorbed by air. Their energy will be finished, their energy will be diminished as they are moving through air, meaning that the ones that are actually detected, despite the fact that they were moving towards the detector, are going to be less. So that's why we wrote this answer, that the sample emits in all directions, but detector only captures emission in one direction. Some emission are absorbed before reaching the detector. Therefore, measured count rate is less than the activity. Thank you.